In our last class, we have seen instructions like jump and label and MCR. So today we are going to discuss about how to create JSR, that is jump to subroutine. Okay, jump to subroutine means, as we have seen some program logics in our previous classes, right? Timer, counter examples. So I cannot write all those different examples in the same block, right? In ladder number 2, because it will take more number of runs and complex logics, right? So what we are doing is we are dividing these logics into small blocks, and we are calling this according to our execution format. Okay, so in which order you want to execute, that way you can call these blocks. For that we are creating subblocks, or also known as subroutines. Okay, subroutine blocks. So how to create this subroutine block? Here you can see there are program files, right? In this we have ladder 2, which is our main block. Then to create new subroutine blocks, click on program, files, click on new. It is showing the number 3. Okay, so any machine 1 or any logic you want to mention, the name you can enter here. And you can do any description if you want. Say okay. Now I'll add one more. New number 4, machine 2 something. Now I opened double click open this machine 1 and machine 2 logics. Now right below also it is showing you the file name like machine 1, 2 like this. Okay, you can select this machine 1 from below, and from ladder 2 what I do is file number 2. I just cut and paste this in the machine 1 logic. Okay, one logic I take here, and another one, second example, cut and paste in another block. Okay, now here I just remove the previous ones. You can call this logic two ways, means with input and without input also. So one example we see with the input JSR. I'm giving one input in main ladder 2. Okay, and which number you want to, file number you have to call, select the file number. So okay. Okay, the next round I'll add one more JSR and the file number 4. Okay, this way you can call this logics. Now save and download this. Now, so here I'm not calling this input here, right? This input is off. So this logic in file number 3, ladder number 3, if I do input here, is your output going on? No, right? Because we are not called this jump to subroutine block, right? So when you give the input, then you see here in ladder 3, you can see output is on. Okay, you can make this on or off. Okay, now if I make this input off, if I disable this, we cannot execute this logic. But in second example, I have called this JSR directly without any input. If you go to that file and right click and modify, you can see it is directly copied. Some logics you have to call on some particular input, and some logics you have to call without any input also, right? So directly you can call this jump to subroutine instructions. Okay. Now it is about JSR here. So today we are going to see next analog signaling. So what is analog signal? Okay, that we'll discuss first. Now analog signal processing. So what is analog signal? Means it's a variable signal which is increasing or decreasing. Variable, right? So we are having some variable parameters like temperature, pressure, speed, flow, level, pH value, humidity, density, etc. Right? So for measuring these parameters, we are having different types of sensors and different units are there. Like temperature is measured uh, in terms of degrees centigrade or Fahrenheit, pressure in PSI or bars. Okay, different units are there, right? So these units are non-electrical signals, but we need electrical signal to convert your okay to connect with your PLC. Okay, your PLC requires electrical signal, so we need to convert this non-electrical signal to electrical signal. So how this is converted from sensor? It is further connected to a transmitter or a transducer. Okay, so transmitter is converting non-electrical to electrical, and transducer is converting non-electrical to electrical, and vice versa. Means electrical to non-electrical also. So there is a difference between transmitter. Transmitter is like a one way. Transducer is a two ways. Okay. Now, so what type of output we are getting here? We are getting two types of signals. One is voltage, other one is current. So voltage is in terms of V, okay, we measure, and for current it is in milliamps. Okay, it is in terms of milliamps. So we are having a standard ranges here, right? Minus 10 to plus 10 volts or 0 to 10 volts for your voltage signal. Whereas for current, minimum minus 20 milliamps to plus 20 milliamps. That is for bipolar signal, right? Bipolar means two polarities will be there, plus and minus. Whereas we can have 0 to 20 milliamps as well as 4 to 20 milliamps, which is mostly used in the industry. Because from 0 to 2 milliamps, your value will be 0 for current signal. Then 2 to 3, there will be some variation. But again, it goes to 0 after 3 milliamps. So up to 4 milliamps, you are not getting a proper signal. So your value will be considered 0. So from 4 to 20 milliamps, your signal will be continuous and your data will be continuous available on your sensor. So that is why we are using 4 to 20 milliamp mostly in the industry. If there is a wire cut, also you will get a 0 as a value. So we cannot identify what's the reason. Okay. So these signals means it can be a voltage or current. Okay, whichever we are selecting. Like for uh, shorter distances, we are using voltage, and for longer distances, we are using current. Okay. So these are further connected to your analog input module at some particular terminals. Okay. We have to check through the wiring diagrams of your analog module, where we have to provide supply and where we have to give the signal. So your voltage or current signal will be having two wires, right? So those two wires plus minus we have to connect on your channels. Okay, it is known as channel 0, 1, 2, 3 like this. Maximum 8 inputs will be there. So channel 0 to channel 7. Okay, will be available on your module maximum. The minimum like 2 inputs will be there on your modules. Okay, then this signal, which is electrical signal 0 to 10 volts, which is varying according to your sensor, right? So when your sensor is sensing the data, it is increasing or decreasing, right? So according to that, your output of this conversion is also varying. So that signal is going to your channel on that particular module. Okay, so which is again converted to A to D. So there is a to D converter on your analog input module, means analog to digital converter. So means that analog value, to store that analog value, we need a word. At least we need one word, like 16-bit data. So here it is converting your analog data to digital format of a 16-bit order. Okay, means in one word it is converted. So for each channel or for one input, it takes one word. Okay, so your addressing format is in a word format. So then this data is going to your CPU. Okay, so we are monitoring, and if it is required, we can also use that data to make some digital outputs on or off by comparing these measured values. Okay. Then, for example, if we are measuring some signal, okay, some temperature like 0 to 100 degrees centigrade, say, which is a raw units. Okay. Then this is further converted to 0 to 10 volts using a transmitter or transducer. Then you can also have in current format, right? That is between 4 to 20 milliamps. Now, this is converted to a value from A to D converter 0 to 32767. Okay, so this is coming at your channel, okay, at your input. That input address we are giving for each input, right? Module. So for each channel, you get this range 0 to 32767 0 to 10 volts. Now, what is actual measurement we are doing here is 0 to 100 degrees centigrade, but what we are getting in the conversion is 0 to 32767. So we need to convert this 0 to 32767 using scale block. Okay, using a scale block, we can convert. That is, again, converted to 0 to 100. Okay, it is known as engineering units. Okay, it is known as engineering units. Means by doing this scaling, we are converting raw units to engineering units to monitor, okay, or to use this measurement for some controlling. Okay. Next, we see how to configure this analog input in our program. So here, first of all, we go to the IO configuration. Double click open. Here in this, you can see we are having one module, fast analog input, analog 2 channel in. You can see here, fast analog 2 channel in means 2 channels of inputs or 2 channels of output. Okay. So when you double click on this, it's a mixed module, means 2 input words and 2 output words. 2 inputs and 2 outputs are there. Okay. So which is a voltage output. Okay. Voltage input 0 to 10 volts, we have to select for this. Okay. If it is giving more details, okay, regarding the module, then you can see the type here. Means you can select some, like we're having this analog input. So I double click open this and double click on this analog. So for this module, it is not showing what type of signal it is. You can select. Okay. So here we are having 16 channel current input. Okay. Current input means 0 to 4 to 20 milliamps or 0 to 20 milliamps. That signal you can connect. Now, so for scaling part, you can go to advanced math. In this, we are having one block called SCP, that is scale with parameter. So select this block. In this, you can see it is showing input, input minimum, input maximum, scale minimum, scale maximum. So input address for which input, right? So double click open this input file. So this is your analog input address I colon 3.0. And it is showing the bit format also. That's for your digital display of your conversion of your value. So we select it as decimal. So you can see here it is showing I colon 3.0 as fast analog input, right? 2 channel input, 2 channel output. You can use this address here, I colon 3.0. It's a word address. We are not using by 0 by 1, right? Now, Input minimum, what value will get? Minimum value is 0. The maximum will get 32767 here. Now we have to scale down to say 0 to 100. And where you want to store this value, like n7 colon 0 or any other memory like n7 colon 50 somewhere, that also you can select. Now this for scaling. Okay. So I'll say this download. Now, so as we don't have any uh, input option, so we use this input table only. So double click and you can enter some value like 1000. For 1000, what value you are getting in the output? And 7.50, it is 3. If I make this 2500, okay, you can see it is changing. 25,000 if you go, right? 32767, you get 100. Okay, if I get out 10,031. So like this converting our data, okay, and what actual measurement we are doing at the field, okay, the sensor, that ranging means like range, minimum, scale, minimum, maximum, we can select. Okay, it gives that output. But after conversion of the electrical to count a digital value, we get 0 to 32767. Okay, so now what else we can do here? An example program like use a comparator. Okay, add one more one. When it is greater than means what? And 7 colon 50 is greater than like 50, then one output should be on. So okay, one output here. And then so the input file, change this to decimal, and here you can change the value like 15,000 something. So 15,000 we are getting 46, right? If I make 16,000, you get 49. You get 50. So 50 also it is not making the output on, right? Because it is greater than 50. If I make 300, but it also is taking 50. 164. Okay, for 17,000 it is taking 52, which is greater than 50. So your output is on. Okay, so this is for scaling. Similarly for unscaling means reversing your outputs. Okay, if you want some output electrical signal, output as a electrical signal 0 to 10 volts or 4 to 20 milliamps. Okay, like we're having control valve. Okay, for opening and closing that valve, or controlling motor speed through a drive. Okay, you can do this unscale block. So the same block I can use here. Advanced Math, SCP. Here input will be N7 colon 50. The scale value, then again unscaling, reversing, right? So what value we are getting there? 0 to 100. We have to scale it to 0 to 32767. And where you want to store that in your output address. So what is the output address here? You can select your output file here. Decimal, this is your output address. Okay. Diagram connect. Yeah, save this. And then now here when we make any update in the inputs, like what output we are getting there, from 15,073 we are getting, right? Or 16,000 we get some other way. 32767 we get 32767. Okay, so this way uh, here, okay, whatever input is there, that is again unscaled, and this is coming at your output. So for the 0 to 32767, your output module will give you the output as an electrical signal between 0 to 10 volts or 4 to 20 milliamps. Okay, this way you can do the scaling here in the panel value.